But on the quiz? Can I see one? I don't have any with me. Okay, so, hey! So the quiz number 5, so it says the object is launched 25 degrees, 25 meters per second at 30 degrees above horizontal, below. Okay. And it takes 3.4 seconds to hit the ground. What was the starting height? All right, so 30 degrees below horizontal means this was the direction when it was launched. Okay, this angle is 30 degrees. And we're going to use a coordinate system like that. Okay, so that's the initial velocity vector. It has a length of 25. And so that initial velocity vector is 25 times cosine. You can do negative 30 or 330. So that gives you 21.65, negative 12.5. And then if you put the coordinate system on the ground right below where it was launched, I mean, you can put it wherever you want, but that's where I would always put it. What do you know? You know the acceleration because it's free fall. You know time final, just time t, I guess. You know the initial position. No, you don't. You know the initial position x component is 0 because the coordinate system is right underneath. We're trying to find P0y. We know Pfy is equal to 0 because it hits the ground. We know all of V0, and we don't know V final. P final, that's what we're just calling Py. Okay, so what equation can you use? You can use Py is equal to P0y plus V0y t plus 1/2 ay t squared. So 0 is equal to P0y minus 12.5 times 3.4 minus 4.905 times 3.4 squared, and solve for P0y. Any other questions? Okay, so last time, yes. Can I have it back? Yes? How do we specify the highest point? Well, the answer is in 2 dimensions, Vy is equal to 0. The y component of velocity is equal to 0. In 1D, just v is equal to 0. So since I didn't specify one or the other, either one of those was fine. All right, last time we were doing circular motion. And what we knew about circular motion was the speed is equal to the absolute value of the angular velocity times the radius of the circular motion. The absolute value of, or the magnitude of the centripetal acceleration is equal to v squared over r, which is equal to omega squared r. So the faster the thing's moving, the bigger the centripetal acceleration. And you know that from, like, if you're in a car and you're going 20 miles an hour and you take a big, wide, round, sweeping turn, you don't feel much acceleration. If you're going 20 miles an hour and you take a really sharp turn, it's a little tiny circle and you feel a lot of acceleration. So that's the centripetal acceleration. Okay, so the last thing we have to talk about related to circular motion is rolling without slipping. And anytime someone talks about rolling at all, they're talking about rolling without slipping, because if it's slipping, it's just like sliding along, you know. So if it's rolling, we're assuming that it's not slipping. And there are 2 facts about rolling without slipping. The first one is that the speed, okay, 2 facts. The speed of the center, capital V sub c, the center of the wheel, is equal to the absolute value of omega r. And the second thing is that the acceleration of the center is equal to the absolute value of alpha r. And these are both parallel to the surface.
Is that the magnitude?
Yeah, that's the magnitude. So you can think of this as like that. To find out information about other points on the wheel, you're going to use that the acceleration of some point P relative to the ground, well, velocity too, but so, sorry, erase that. Let's do velocity first. So velocity of some point P relative to the ground is equal to the velocity of that point P relative to the center of the wheel plus the velocity of, what does relative motion say on this one? That's right, center relative to ground, exactly. And the same thing is for acceleration. The acceleration of p relative to the ground is equal to the acceleration of p relative to the center plus the acceleration of the center relative to the ground. Okay, so where do these terms come from? This one and this one come from circular motion, because all of those circular motion equations are assuming that the center is fixed, and that's what it means to calculate something relative to the center. And these two come from what we know about rolling without slipping. Okay, so let's say we have a wheel that's rolling with some arbitrary positive angular velocity omega and also an angular acceleration alpha. And this wheel has a radius of r. And we want to calculate, there are 2 points we want to calculate stuff. So I'll call this point B for the bottom of the wheel, and I'll call this point T for the top of the wheel. And we want to calculate the velocity vector at the bottom, the acceleration vector at the bottom, the velocity at the top, and the acceleration at the top. And we're going to calculate the vectors. All the equations we're using have to do with magnitudes of vectors, so we're going to have to think about directions on top of using the calculations for the magnitudes. So first of all, if the angular velocity is counterclockwise, like it is here, which direction is the center of the wheel moving? Yeah, it's moving to the left. That you're just sort of thinking physically about what's happening. And if the thing has an angular velocity counterclockwise, that also means that the acceleration of that point C, the center, is to the left. Anybody have any thoughts about the relative speeds of B and T? Which one's going to be moving faster, slower? Are they going to be the same? They're not going to be the same. If they were all the same, this thing would, if they all had the same velocity, this thing would just be sliding. Can you see that?
Oh, it would be the same absolute value of velocity. But they would be opposite signs.
Okay, that's an interesting thought. So if the center was still, that would be correct. Okay, if the center was still, the top and the bottom would have the same speed.
Also moving forward.
Yes, but the center isn't still; it's moving this way.
Top's moving faster.
Yes, the top is moving faster, and the bottom, actually, if you think about what it means, like if you had to come up with a definition for not slipping, yeah. Yes, that's right. Yep, That's a perfect thought, yep. So if you had to think about what it means for something not to be slipping, okay, what does it mean for that point on the bottom if it's not slipping? Well, one of the things it means is that whatever the velocity of this point is on the ground, that has to match the velocity of the point that's in contact with it, right? Like if this is going 2 miles an hour and the ground is at rest, then that means exactly that point is sliding along the
So
ground.
you would take B minus C or B plus C and B, like, that's what the actual speed of, if it was still,
Yeah.
like B would be a speed, but then you have to add the C to it.
Yeah, right. So all I want you to notice right now is this seems a little weird, but for this not to slip, the velocity of that point B has to be 0. Okay? So just instantaneously, every point that's in contact with the ground, only at that one instant is at rest. It has no velocity. We'll calculate that. Okay? And so if this has 0 speed, and this has some speed that way, that's equal to omega times r, your next guess might be that this is the fastest speed of all of them, and that's how it is. Okay, so the top is the fastest point on any wheel. The middle has the speed omega r, and the bottom has 0 speed. And actually, if you take a picture of a wheel that's rolling with just the right exposure length, what you'll see, like a bicycle wheel, so where you have spokes, you'll see very clear pictures of spokes down here, and then they'll get blurrier and blurrier, and up at the top it's a total blur, you know. So yes.
At the base of the wheel is motionless, right?
Yes, it still has the centripetal acceleration, but it doesn't have any horizontal acceleration or velocity. Okay, so let's calculate that. So the first calculation has to do with the bottom of the circle. So we know that the acceleration of the bottom relative to the ground is equal to the acceleration of the bottom relative to the center, plus the acceleration, velocity. Keep doing that. Velocity of the bottom relative to the ground is equal to the velocity of the bottom relative to the center, plus velocity of the center relative to the ground. Velocity of the center relative to the ground, its magnitude we know is equal to the magnitude of omega r. And we already figured out that if omega is counterclockwise, the velocity of the center needs to be in the negative x direction. So this is going to be negative omega r 0.
Which one gets more confusing?
It would if you use this coordinate system, but the way to deal with that is just to tilt the coordinate system. So that, yeah, so you still have your x-axis parallel to the surface, and then everything's exactly the same. Yes, you would have to, yep. Not the Pythagorean theorem, sine and cosine. Yep. Right. Yeah, trigonometry. Okay, so we got that part. Now we need, this is, yes. And then the velocity of the bottom relative to the center. Well, that's also the absolute value, the magnitude of that velocity is also omega r. This is circular motion. So this is an easy thing to get confused about. These two things are identical, right? It's the same formula, but they have those formulas for different reasons. This is because of what we know about a point that's in circular motion around a fixed center. And this is because of what we know about the velocity of the center of a wheel in rolling without slipping. Yeah. You know, it's the calculation for the velocity of the center relative to the ground comes from circular motion. You just have to, and so it's not just a coincidence that they're the same formula, but it takes more thinking than we've done on this so far to see why they're the same. So for you, you just need to remember that in rolling without slipping, the center has this speed. Okay. And you need to remember that in circular motion, a point outside the center has this formula. Okay, so this is from rolling without slipping. This one is circular motion about a fixed center. Okay, well, if we're talking about circular motion around this fixed center and we have our omega like this, what's the direction of the velocity vector of B? Yep. So that's the velocity of B relative to the center. And so now our relative motion equation says velocity of B relative to the ground is equal to velocity of B relative to the center plus the velocity of the center relative to the ground. Velocity of B relative to the center is the one we just did. That's positive omega r 0. The velocity of the center relative to the ground, that's this one. So question? Okay, so velocity of B relative to the center is this. Velocity of the center relative to the ground is this. And so the velocity of the bottom is 0, 0.
And that's only at that one point.
Only at that one point, yep.
That was neat.
Yeah, exactly. I know, that's all of you. Even the ones trying to play it cool right now.
You just put a little explosion.
I'm not your trained monkey. Okay, so now we're going to calculate the velocity vector at the top of the circle, top of the wheel. The approach is the same. The velocity of the top relative to the ground, that's what we're trying to find. is equal to velocity of the top relative to the center plus the velocity of the center relative to the ground. Dang it. Okay, let's do acceleration first. Okay, so the acceleration of the bottom relative to the ground is equal to the acceleration of the bottom relative to the center plus the acceleration of the center relative to the ground. The acceleration of the center relative to the ground in absolute value is absolute value of alpha times r. And if the angular acceleration is counterclockwise, then that acceleration is to the left. So we have negative alpha r And does that one come from circular motion or from rolling without slipping? Good, yep. And now we're going to do the acceleration of B relative to C. Okay? And this one is circular motion. Okay, so this one, we're assuming that the center is fixed. And we're trying to figure out the acceleration of that point. More? There? Oh, yeah. That's how you would have felt if you would have been listening when I arrived at that result. Yeah, exactly. Truth bomb. Yes. When? Oh, that's just a different way of writing that vector. I'm trying to keep reminding you that there's two different notations for that. More often, physics people use that IJ notation, and engineering people use that vector notation. I'm just trying to, when I remember doing both. But do you remember that? So that I just means that's the x component. Okay. So, how are we going to figure out the acceleration of that point bottom? Well, this is, yeah, so this is the same as the stuff we've been doing in lab with circles and the stuff we did last time. So the way this works is, if we're assuming that that center is fixed, which we are for now because that's what it means, B relative to the center, it means we're assuming the center is fixed. The velocity vector is that way. Which way is the tangential acceleration? Same way, because omega and alpha are the same direction, so it has to be speeding up. The centripetal is always the same way. That's always from the point towards the center. Okay, so now we have all the directions, and now we can just use the equations the centripetal acceleration magnitude is equal to omega squared r. And so what's the centripetal acceleration as a vector? This is the centripetal, so it's the one going up, so it's 0 omega squared r. Or omega squared r. And then the magnitude of the tangential acceleration is alpha r. And as a vector, what's that one? Yep, alpha r 0. Or alpha r times I unit vector. So the total acceleration of B relative to the center is, add those two together, you get this plus this equals alpha r omega squared r. And now we can use relative motion. Acceleration of the bottom relative to the ground is equal to acceleration of the bottom relative to the center plus the acceleration of the center relative to the ground. We've calculated both of those now, so bottom relative to the center is alpha r omega squared r. Center relative to the ground is negative alpha r 0. Bless you. And so you end up with 0 omega squared r for the total acceleration of the atom relative to the ground. So the velocity of that point that's touching the ground is 0. The acceleration is not 0, but what is 0, so this is the second requirement for rolling without slipping. At the contact point, let me write that. At B, the acceleration parallel to the surface is 0. So if that contact point had an acceleration parallel to the surface, that would be the wheel and the surface slipping against each other, okay? It can lift up and down, and that's what that centripetal acceleration is doing. It's making it turn to stay in a circular path, but it's not starting to slide. Any questions about that? Yes. So now we're going to do C and D on the board. Anybody have any questions before you start working on this? So go ahead and try to work through this and let me know if you have questions. And when you're done, I'll go through it too. Okay, so for part C, the velocity of the top relative to the ground is equal to the velocity of the top relative to the center, plus the velocity of the center relative to the ground. So the velocity of the center relative to the ground, since the rotation is counterclockwise, this is just negative omega r 0. And now the velocity of the top relative to the center, that's circular motion around a fixed center. So the center's fixed. The angular velocity is this way, so the velocity is this way. That's the velocity of the top. Oops, this should say center. Top relative to the center. And so velocity of the top relative to the center is equal to negative omega r 0. So the velocity of the top relative to the ground is negative omega r 0 plus negative omega r 0, or negative 2 omega r. So the top of a wheel is always going twice as fast as the axle. So like when you're riding your bike, top of the wheel, if you're riding your bike 10 miles an hour, the top of the wheel is going 20 miles an hour. That's how it always has to work. Any questions about the velocity part? Yes. Yep. If you're just following a line from the top to the bottom, these vectors get weirder if you take a point that's a horizontal motion from the center, because then you still have the horizontal velocity of the center, but you have vertical components to the velocity of the point relative to the center. Okay, and then the angular acceleration, the acceleration, part D. Acceleration of the top relative to the ground is equal to the acceleration of the top relative to the center plus the acceleration of the center relative to the ground. Acceleration of the center relative to the ground is negative alpha r 0. No, this is the one, so this is just from the rolling without slipping. So these don't have any names. Those are just facts. Well, they do derive from that in a little bit of a complicated way. I didn't go into the derivation, but that just comes from, but that's the one that looks similar to the tangential acceleration. And then the acceleration of the top relative to the center. There's two of them. There's two components here. The velocity is this way. The tangential acceleration is that way. The centripetal acceleration is this way. And you get is the acceleration of top relative to the center. Nope. Yes. Is equal to negative alpha r. That's the tangential part. 0. Plus 0 negative omega squared r. So those combine like this. And so the acceleration of the top relative to the ground is equal to negative alpha r negative omega squared r plus negative alpha r 0. So negative 2 alpha r negative omega squared r. So if the thing has an angular acceleration of alpha, the center is moving this way with an acceleration of alpha r. The bottom doesn't have any horizontal acceleration because it's not slipping, but it has a centripetal acceleration up. And the top has an acceleration horizontally of twice the acceleration of the center, and then a centripetal acceleration down. Okay, so now we're done with particle kinematics. Now we're going on to particle kinetics. Those words are pretty similar. Okay, so kinematics with the extra ma in it means you're just describing the motion. Yeah, right. But you're still going to forget it, so I'm still going to do it like 10 more times. So this one, kinematics, is there. We're not including the causes of the motion. No forces or mass or anything like that. Kinetics combined, so kinematics is part of kinetics, but now we're also going to include causes of the motion. And the causes that we're going to talk about are mass and force. So, I don't know. This is a way to keep these straight. I don't know if it's the best way, but kinematics is the more complicated word and the less complicated subject. Kinetics is the less complicated word and the more complicated subject.
When are we getting into air resistance?
We're never going to do calculations with that. So the only way air resistance comes up is in sort of, we talked about how the different things affect air resistance, surface area, mass, that all those. And so it only comes up in saying, like, this is a case where there's a lot of air resistance, and so the techniques we have don't apply very well to it, Okay, so we need to introduce two new quantities. And those are mass and force. I'll start with mass. That's sort of the simpler one. So mass is always, mass isn't a vector quantity. There's no such thing as what something's mass is in a certain direction. It's always a positive scalar. Positive number. And it's a measure of how hard it is to change the object's velocity. If a marble is coming towards you on the table, it's easy to change its velocity, change its direction and or its speed. So that's easy to change velocity. And that means a marble has a small mass. A semi, if that's coming to you across the table, it's going to be hard to change its velocity. No, these are good tables. Yeah. And so a semi has a big mass. So the more mass an object has, the harder it is to make the object. So what are the two things that define an object's velocity?
Change direction.
Yep, the harder it is to make the object change directions, and or
Speed.
Yep, change speed. Speed up or slow down. That's why good football players are always really big. The defense is trying to change their velocity. And the more mass the player has, the harder it is to change their velocity. One thing to notice is when we talk about weight and mass in sort of everyday speech, we talk about them as being the same thing. But weight and mass mean different things. They have different units. So weight and mass are different things. Weight is the force applied to an object by gravity. And the weight does depend on the mass, and that's why we, relate those two things. The more mass an object has, the harder gravity pulls on that object. But if, most bathroom scales, I think, have a switch on the bottom that'll switch from kilograms to pounds. Okay, pounds is a unit of force. Mass, well, kilograms. Kilograms are a unit of mass. And so what the scale is really measuring is the force that your feet are putting into the scale, which, as long as you're not touching anything else, is equal to the force that gravity is putting on you. The scale isn't directly measuring your mass. So the scale is only right about your mass if you use the scale on Earth. If you took the scale to the moon and weighed yourself, the scale would give you an accurate reading of your weight, the force that gravity applies to you, but a totally inaccurate reading of your mass, because it's making that conversion based on assuming Earth's gravitational pull. Okay, SI units for mass are kilograms. That might be the only SI unit that has a prefix in front of it. You'd think maybe grams would be more natural, but here we are. And we'll abbreviate that kg. Kevin Garnett. Okay, a force. This is the more complicated one to define. This is a vector quantity. And that means it has a magnitude and a direction. You can apply the same force, like I can apply a force up on the table or down on the table. They can have the same magnitude, but they're different forces. And you can just think of a force as the intensity of a push or pull on an object. Mathematically, you can think of a force as defined by Newton's second law. I'm just going to abbreviate that N2L, because I'll write that all the time. And Newton's second law says, in any inertial coordinate system, so first of all, for this law to hold, you have to have an inertial coordinate system. And the meaning of an inertial coordinate system is that it's not accelerating or rotating. F net, the net force vector, and I'll tell you what all these mean in a second, is equal to the mass of the object you're looking at times the acceleration of the object's center of mass. So F net is the sum of all force vectors acting on the chosen object M is the mass of the chosen object. And ACOM is the acceleration vector of the object's center of mass. Okay, so Newton's second law is, you've heard F equals ma before, and that's Newton's second law, but there's some subtleties to it that you have to remember to use it right. This is the most important equation in this class. We use it in almost every problem from now on. So I want to say, I'll say more about inertial coordinate systems, but that's sort of a weird idea. Like, what does it mean for the coordinate system to not be accelerating, not be rotating? I think the easiest way to think about a coordinate system is to think of it as a video camera where you're taking your measurements through this video camera. Okay, so based on what the camera sees, you're deciding what an object's velocity is at any instant, what its acceleration, position are at any instant, okay? But if that camera is mounted to something that's accelerating or mounting to something that's rotating, you're going to get a sense of the motion of the objects that it sees that will not satisfy Newton's second law, okay? So actually, I'm going to say more about that right now. So let's think about so here's an inertial coordinate system description. So let's say we have one of those things that they always use in astronaut movies, where the astronauts sit in this chair and they get spun around in a circle. His face is just being stretched. You know what I'm talking about? Yeah. You all know what I'm talking about. So the reason they do this is to get people used to dealing with high G forces. Big accelerations, to get them used to big accelerations. And when this thing is moving full speed, it's just moving at a constant speed. Where does the acceleration come from if the speed isn't changing? That's right, there's a high centripetal acceleration, and that's the acceleration that this person feels. Okay, so let's think about a coordinate system that's mounted like this. Let's say that's X, that's Y coming out towards us, and then Z up. And this coordinate system can do two different things. It can stay fixed, and then every revolution around, it sees the astronaut one time, right? So the camera just sees like, ah, Mom, you know, help me. This isn't the YWCA. Or the coordinate system can rotate with that arm. And if it rotates with the arm, what does the coordinate system see? It's just looking at the person the whole time, just like, ah, just nonstop. Ah. Yeah, right. So if the coordinate system's fixed and the person goes by every, okay, well, so say there are forces sensors in the chair that are measuring the force of the person, and they're measuring that because of this, because the chair has to keep him moving in a circular motion, there's always a big force on that chair. So that's measured. And now think about the camera measuring the acceleration. Okay, so in the case where the coordinate system is fixed and the astronaut just goes by, that camera measures that that person has a big acceleration. Okay, the camera that's rotating with the person, as far as it knows, the person has just a constant position. The person's just sitting right there. Okay, and so in the fixed case, the camera measures a big acceleration for the astronaut. In the case where the camera's rotating, the camera doesn't measure any acceleration at all. And so think about Newton's second law. Newton's second law says, take the forces, the weight force plus the force applied by the chair, it has equal to mass times acceleration. In the case where the camera is rotating and no acceleration is measured, this would obviously be out of whack. It would look to somebody observing this motion through the camera like Newton's second law doesn't apply. So in the case where the camera is rotating, it looks like Newton's second law doesn't work. That's the idea of an inertial coordinate system. This would be a non-inertial coordinate system. Well, we only have 5 minutes. Let's watch a video that sort of shows how this works. Whoops. Wow, that was a good year for bus fails too. That's saying something. Meredith, you should watch this too. Okay, wait. So it doesn't look real, right? It doesn't look real, but it is. Yes? Yeah. Yeah, so this video serves two purposes. The physics purpose it serves is you look at it and you're like, that doesn't look real, because your idea of what is real, like basically you're using Newton's second law in your head, and that looks like it violates Newton's second law. it looks like it violates Newton's second law because the camera is mounted to the bus. And so when the bus takes this huge acceleration, your coordinate system says that person has this huge acceleration that happens without any force, okay? Like just suddenly the person flies for an instant. And that violates Newton's second law. What's really happening is the bus has a big acceleration, and so your coordinate system, that camera, is like if you try to, in your brain, calculate Newton's second law, it says it was violated there. Okay, so that's the idea of inertial, non-inertial coordinate system. Newton's second law doesn't work in every coordinate system, only ones that are not accelerating and not rotating. Yep.
So why doesn't the bus obviously the bus is a big bump, but then she started floating and the bus goes down. Why isn't that?
I don't know what happened there, but there's usually just like a I don't know what made the bus. It looks like the bus must have accelerated down really fast.
Yeah.
Like right. Yeah, well, it must have been something other than free fall. You're exactly right. If the bus just did nothing but go into free fall, then that wouldn't happen. Yep. It must have hit something that made it jerk down somehow.
That's one last thing that guy always says.
To be honest, I probably wouldn't end up doing it. Oh, screw those guys. What have they ever done for me?